5 things everyone should know about ancient oceans. Number 4. At the end of the last ice age, sea levels rose around the globe by the height of Big Ben.
Roughly 20,000 years ago, the world was in the midst of its last ice age. So this is when the large northern hemisphere ice sheets extended way down beyond northern Europe and well into the United States. At about 18,000 years ago, the Earth started to warm up. And we know from ice core records that the carbon dioxide levels in the atmosphere started to rise at that time as well. The consequences of this were that we began to see melting of these ice sheets and ice caps. Over a period of about 5,000 years, from about 16,000 years to 11,000 years ago, we saw a rise of about 90 metres or so, and that's basically the height of Big Ben. It didn't happen all at once, and it didn't happen gradually. It happened in pulses. And some of these pulses were really very fast. Some of the sea level rises equated to about 10 millimetres per year. And that's much faster than any of the sea level rise that we're seeing today.
One way of working out how high sea levels used to be is by looking at corals that live in tropical seas.
So, for example, scientists have used corals from Barbados and Tahiti to track sea level back through time. So these corals, they have algae inside them that they use to get their energy, and they rely on light. So we know they're going to be growing in really shallow water. So by dating the corals, we can know when they were right at the surface of the sea. So that's a way of tracking where sea level was. So one way we can use to actually date these corals is by using the radioisotopes that they have inside them. So these radioisotopes are radioactive elements, such as uranium, for example, trace amounts of natural uranium that we find in these corals. By measuring how much of these different radioisotopes are in there, the ratio of the different isotopes, we can calculate how old these corals are. So it's something that paleoceanographers like myself think about a lot, where this carbon dioxide comes from. And one of the key targets are the oceans. So the ocean's actually quite a big reservoir for carbon. It can lose its carbon quite quickly. So we think it might be something that could release over these sorts of timescales. And so one of the things that we try and do is look at where the carbon might be and most likely in the deep ocean. And it links in with the changes in ocean circulation that we see over these sorts of timescales.
During the last glacial, sea ice was much more extensive over the oceans than it is today. And the sea ice acts as a big blanket, insulating the ocean from the atmosphere and vice versa. And so when temperatures were warming up during the deglaciation and the sea ice extent was becoming less and you have less sea ice, suddenly the warm waters from the ocean are exposed to the atmosphere, and the CO2 that's been building up in the ocean when the ocean circulation was slower, as the circulation speeds up, that CO2 is released to the atmosphere. So it's one process, the involvement of sea ice, that helps with this increase of CO2 to the atmosphere and therefore the warming that we saw coming out of the deglaciation. So sea ice is very important to the whole global climate system because it influences what we call the albedo, the reflectivity of the surface of the Earth. So when you have lots and lots of sea ice is very white, it's very reflective. It reflects back a lot of the sun's energy into the upper atmosphere and back into space from the surface of the Earth. So necessarily when you reduce the amount of sea ice, you're left with more ocean, and ocean is darker and it absorbs heat from the atmosphere more, so you're reducing what we call the albedo.
What we try and do as paleoclimatologists is try and find analogues, so sort of comparative events that happened in the past, that we can use to predict what might happen in the future.